Hello, good morning, everyone. Is that
Hello.
showing in, yeah, slideshow.
Yep, yep.
Right. Okay, so very pleased to be here. Thank you so much for the invitation. Today I'm going to be talking about the work we've been doing in the area of building hydrogels from mixtures of polymers and cyclodextrins. So cyclodextrins have already been mentioned at this conference. They are macrocycles of glucose units. There are three main types, which are easily available also in modified versions, which are the alpha, beta, and gamma, which have 6, 7, and units respectively. The number of glucose units obviously means different sizes of the molecules, which have this torrid shape with a cavity in the middle, so that the size of this cavity increases with the number of glucose units. So why are these molecules so well known? Why are they useful? And why do I do so much work with them? Is because of this cavity in the middle that is slightly apolar. It can encapsulate a number of small molecules, in particular drugs. So they have been used widely in the pharmaceutical industry to solubilize drugs, but also to solubilize perfumes, flavors, and all sorts of things. So depending on the size of the molecule, we can have different ratio of the complexes. So these are so-called host-guest interactions, and they belong to a wide family of similar molecules, which where you have a guest and a host. What I'm particularly interested in, and what I will be talking about today, is the capacity of these molecules to also thread onto polymer chains, as you can see at the bottom. And this is something that has been known for a long time, since the seminal work of Akira Harada in the early 90s. So those cyclodextrin, by threading onto polymer chains, form these so-called pearl necklace structures, as illustrated at the bottom. And these structures are very useful building blocks for further supramolecular structures, and in particular gels, as I will be describing today. Just a very quick snapshot to illustrate the fact that, yes, I've been interested in these molecules for a long time. So on the left-hand side, you can see some work using cyclodextrins just to encapsulate drugs. In that case, we're looking at their interaction with gram-negative bacterial membranes. The fact that they can form inclusion complexes also with surfactants mean that we can modulate the morphology of these aggregates, so of the shape of the micelles, going from long micelles to short micelles or vesicles, depending on the these host-guest interactions with surfactants. On the right-hand side, this is some work where we've been interested to look at what happens if we thread different types of cyclodextrins on the same chain. That leads to interesting competitive or cooperative interactions, and we've been looking at the kinetics. This is what is shown at the bottom here. But really what I'm going to be focusing on today is the capacity of these cyclodextrins, and in particular alpha cyclodextrin, to thread onto polyethylene oxide to form these pearl necklaces structures. So we call them pseudo-polyrotaxanes because the end of the chains are free for the cyclodextrins to move in and out, rather than having stoppers at the end. In that case, we would call them polyrotaxanes. Just in case you're completely new to this field and you want to learn some stuff, these are two review papers that I have come across, which show the breadth of applications of generally these interactions between cyclodextrin to form supramolecular structures. So the one at the top, if you look at the graph on the left-hand side, I think perhaps that's the one thing to remember if you want to start working with cyclodextrins, is that the smallest size cyclodextrins, so the alpha, is very good at forming inclusion complexes with PEG, polyethylene oxide, and from that structure, through hydrogen bonds between the alpha cyclodextrins that are on different chains, these connect together, forming junction points for a network or for a hydrogel. The beta cyclodextrin is the one that is most known to the pharmaceutical industry because it has the right cavity site to interact with a vast number of drugs and other molecules. So the strategy to build gels from that slightly larger cyclodextrin would be to graft beta on half of the polymer chain and graft a guest molecule on the other half of the polymers. And so through a zipping process, these would then form a gel. And there's another review also published in Coordination Chemistry Reviews just the year before, which looks at a slightly wider range of materials with things like 3D printing and paints, and looking at the self-healing properties of these gels, on which I will touch on later on. So I will go through short projects which were done previously in my group, and then finish with a current project. So these first two projects sort of set the scene. So as I explained, with alpha cyclodextrin threading onto PEG chains, we form these zones of connections with the alpha cyclodextrin interacting through hydrogen bonds. And so these then act as crosslinks for a network. So we get these white gels, as you can see on the right-hand side. So our first question for this project was, what happens if the PEG chains are attached to a surface? And in this case, if the surface is a nanoparticle. So we expect that the cyclodextrin will be able to thread onto the polymer chains in the same way, then connect together and make a gel. But then that would mean that we have effectively incorporated nanoparticles in a gel structure, and then we can combine the properties of the nanoparticles with the advantages of having a gel matrix. But is that possible? What does that change to the properties of the gel if we do manage to make gels in this way? So this was a collaboration with Vitaly, who kindly provided some nice silica nanoparticles, which had been previously reported. So they're very monodisperse nanoparticles onto which PEG chains are grafted. And we looked at two sizes of PEG, so 750 and 5000. And we also had different grafting densities. So this first slide with data is a little bit busy, so let me explain, because this is an important aspect of these host-guest interactions between alpha cyclodextrin and polymers. So as you can expect, for the cyclodextrin to thread onto the chains and then form connections, it takes some time. It is a kinetic process. And there's a very, very simple technique to follow the kinetics of this process, is simply using turbodimetry. Because what happens is, as the cyclodextrin thread onto the chains, nothing much happens. And this is the first phase where no increase in turbidity is detected. And as the chains start to aggregate through the hydrogen bond between alpha CD on adjacent chains, which then form the crosslink of a network or lead to phase separation, we get this huge shoot up in the turbidity. So we can follow the kinetics of the complexation. So we've done this here, and we looked at the effect of temperature. So perhaps the first comment to make before I look at the different species that we have studied is the fact that temperature has a huge effect on the complexation, and perhaps slightly counterintuitive, as you increase the temperature, so going towards the yellow curve, the complexation is actually slower. It's slightly counterintuitive because you would expect temperature to increase the diffusion rate of the host and the guest in this case. But what temperature also does is that it weakens all the interactions that are responsible for the further aggregation and complexation simply. So hydrogen bonds are weakened, and therefore the process is slower. So what we've looked at on this slide is what happens when we have, so on the left-hand side, PEG that is attached to a nanoparticle. So we just have one end of the PEG that is available for threading rather than having the two ends. And then we also have on the right-hand side PEG with a bulky end group at the end. So again, in this case, there's only one end of the polymer that is accessible to the alpha cyclodextrin. So what happens in that case? And we compare that to PEG that are free on both sides, which is usually the way we work with these complexes. And so to compare all these data, I have plotted in the next slide the threading time, which is that time when the cyclodextrins are simply threading before further aggregation and gelation takes place. So this is what it's shown here. So it's the threading time as a function of temperature. And there are two comments to make from this graph. The first one, as I explained earlier, is that we have a clear effect of temperature on the aggregation process, on the complexation process, therefore. But we have clearly two groups of polymers. So this is the second comment. If you see the curves on the top, that's the one where only one end of the chain is available to alpha CD. And the other group at the bottom, the two ends are available. And you can see that the threading times are shorter, and also they're less dependent on temperature. So there's a much larger effect of the temperature on slowing down the process if only one end of the polymer is available for the complexation. So I'm not going to get into the detail of this. This is, we can extract some thermodynamic parameters using transition state theory, where we consider the complexation as a pseudo first order process. We can see from the value of the Gibbs free energy that these are all favorable, thermodynamically favorable reactions, and that actually the ones where the PEG has only one end available have a slightly lower Gibbs free energy. So the process is more favored when only one end is available, despite being kinetically slower. If we build a phase diagram, so this is a typical phase diagram for this type of systems at different composition of the polymer and the alpha cyclodextrin, in this case, the polymer is attached to nanoparticles. We get a phase region of the phase diagram where we get gels, and in other regions, we may get phase separation or weak gels or liquids. And looking at the rheology of these gels, well, one first thing to say is, again, this is quite characteristic data of this type of polymers. We have a very structured and stiff gels with G prime, the elastic modulus, being fairly independent of frequency. It is actually quite high values of the modulus, so these gels are quite stiff. And if we compare on the left-hand side, the case where the polymer is attached to the nanoparticles, the values of the modulus are one order of magnitude higher than what we would get if the PEG chains are not attached to a nanoparticle, which in a way is expected because the nanoparticles are reinforcing the network. They're part of the network because they are part of the cross-linking process through the PEG chains. And I should say also that if we used shorter PEG chains or lower grafting density, we didn't get gel. So obviously the length of these chains and the density of the nanoparticles is important for the formation of gel. So this is the picture from this first project. The second one I will go very briefly through, but it came from the question of how can we use this process to combine the properties of two different polymers. So if we simply graft PEG this time on another polymer backbone, can we then combine, have a synergistic effect between two polymers? So for instance, here using chitosan, which has a number of interesting properties such as mucoadhesion and others, can we then make a gel where it's incorporated in a network? And this is a project where, again, we use the good services of Vitaly and his group. So they pegylated the chitosan for us. As expected, the solubility of chitosan increases even at neutral pH, and there's other data showing that even above neutral pH is improved when it's pegylated. Again, building a phase diagram where we mix this grafted polymer with alpha cyclodextrin, we find a region of the diagram where we get this typical white gel phase, and other regions where we either have a weak gel or liquid or a biphasic system. What I really wanted to highlight in this work, because I'll come back to that later in the final project that I'm going to be talking about, is that there's a very simple experiment or typical experiment that is used to detect the presence of these pseudopolyrotaxanes. So in other words, how do we prove that the gels are made because the cyclodextrins have threaded onto the polymer chains? And so the reason we can detect them simply is because they arrange in a hexagonal phase through this hydrogen bonding between the cyclodextrins. And these give rise to very specific reflections in an XRD pattern. So we call them the channel type crystalline structures. So these are actually sort of microcrystalline regions. And you can see here, there are two intense peaks at 20 and 22.6, which come from the 210 and 300 reflections from the hexagonal lattice. So it is the proof that we can use to show that we actually have pseudopolyrotaxanes. And as you can see, the cyclodextrin are arranging tail to tail and head to head to maximize the hydrogen bonds between the smaller and the larger rim of the toroid shape. And I'll also come back to that later. Again, looking at rheology, you may spot that we get values quite similar to what I was showing earlier. That in this case, we use quite a low amount of polymer. So you can see at the bottom from 0.2% to 0.4%. Obviously, the concentration of alpha cyclodextrin is quite high, but we can see that as we add cyclodextrin, we're not improving the properties of the gel. So there's always a bit of tuning and tweaking to get the correct properties. And finally, another really characteristic of all these alpha CD PEG gels is the fact that they are healing or shear thinning. So if we apply a high shear to sort of destroy the structure of the gel, and then we remove the shear or we make it very, very low, you can see how quickly the gels recover, because these are all dynamic junctions, and it's obviously the advantage of this type of gel. And we can do that several times. We do get a little bit of reduction after several cycles, but it's quite reproducible. Okay, so I'm coming onto the final project, which is a current project with my very talented PhD student, Shang, and a colleague at King's based in chemistry, who is an inorganic chemist. And in this last little short story, I want to show you the other possibilities that cyclodextrin offer when we modify them. So as you can see, obviously the glucose units have a number of hydroxyl groups that can be modified. So this one in position 6, the primary hydroxyl groups are very nucleophilic, and they're quite easy to modify. And that obviously can lead to several advantages in terms of molecular recognition and other things. And we use this to improve the stability of nanoparticles, as I'm going to show. So we were making copper sulfide nanoparticles. I'm not going to spend much time on that. We make them from a single source precursor, and this is all the work of my colleague Graham Hogarth. And so through decomposition in water, we obtain these really nice copper sulfide nanoparticles. And these have all sorts of electrical and optical properties that are interesting for therapy and imaging diagnostic. So the idea was to use cyclodextrin to modify the surface of the copper sulfide nanoparticles by immobilizing the cyclodextrin on the surface, improve their dispersion and stability, and perhaps lead to further functionalization. And just to say where that came from, the original idea just came from this paper where the authors modified gold nanoparticles with the native beta cyclodextrin, so not even modified, if I recall correctly. The beta cyclodextrin can easily encapsulate different types of species. In this case, they tested it with cholesterol, so it could capture cholesterol, and through a change in the surface plasmon resonance of the gold, very, very low levels of cholesterol could be detected. So this was used as a detection method and could be applied to a number of molecules. So this is where this idea of decoration came from. But obviously, because of all the work I've presented before, I also thought, well, it would be nice to do also gels based on this motif that I've been showing before, and so combine both. And this is how my student Shang is sort of presenting the whole idea for the platform, where we have these copper sulfide nanoparticles, which are embedded in a gel with all sorts of advantageous properties that come from the gel, that come from the copper sulfide and the cyclodextrin. So how do we connect the cyclodextrin onto the surface of the copper sulfide nanoparticles? So an obvious thing to do, so how do we modify it? What do we choose as a group, functional group, to modify the nanoparticles? So copper sulfide obviously is thiophilic, so we thought a better cyclodextrin would be one that is thiolated. So this is why we thiolated, or Shang's thiolated beta cyclodextrin, simply mix them with the copper sulfide nanoparticles. The thiolation here is in, as I said before, in just one position of the glucose. We go through an iodo intermediate and we get this thiolated beta cyclodextrin. And indeed, we get a good improvement in the dispersion of the nanoparticles. So instead of having aggregates and large size here on the top, you can see that when they're simply mixed with this beta cyclodextrin, we get a better dispersion of the nanoparticles. So that was the first step. But the second step was to put all of this in hydrogels, and this is why where I didn't thought through the project quite properly, because if you've been following, it is actually the alpha type of cyclodextrin that is good to make the gels simply through threading on a PEG. So therefore we reverted to the thiolated alpha CD, but luckily Shang had got quite some experience with the beta, and so he was quite good at, he could easily adapt the procedure to alpha. And if we do this, mix thiolated alpha CD with PEG, leave overnight, nothing happens. We add the nanoparticles and we heat. I'll talk about this in a minute. Then we get these nice green gels because of the copper sulfide. If you look at the effect of temperature, you can see that if we do nothing or leave the sample in the fridge, nothing happens. If we leave it at room temperature, we only get a gel after 2 days. If we heat it, we accelerate the process substantially. And after 15 minutes at 60 degrees, we get a gel. So what we have here is quite different from what I had been describing in the first part of my talk. We most probably have the formation of disulfide bridges, which I've been describing in the previous talk. So through oxidation of the thiol groups, we are operating at high pH because of the lack of solubility of the thiolated cyclodextrin. I should have mentioned that. And the oxidation process is facilitated at high temperature. So we probably have a gel that is actually formed by disulfide bonds. So I'm going to go quickly through the rheology so we can follow the process over time. Those gels are shear thinning because the junctions are dynamic. We get gels also with nanoparticles inside, and the gels are better if we let them slowly gel rather than heat them up quickly, which is kind of expected because the junctions are going to be more homogeneously dispersed throughout the sample. And we get a small effect of increasing the elastic modulus by adding the nanoparticles. So I just want to finish off on the mechanism of gelation because it's quite different from the usual native alpha cyclodextrin with PEG gels. So because we suspected that most of the gel was based on these disulfide bonds, we used DTT as a reductant that can cleave those junctions. And indeed, if we add DTT to our gels, very quickly we get a gel to salt transition. We can follow this with rheology. So if we add DTT, we get a decrease in G prime and G double prime. And if we wash off the DTT, we can actually recover the gels with an increase in G prime. So really our gel is probably based on these disulfide bonds between cyclodextrin. Now the next and final question that I'm going to address is, we then had a doubt about whether those cyclodextrin were indeed whether this cyclodextrin were indeed threading onto the PEG. And so this is where, if you remember, I showed you we usually identify this by using XRD and finding these reflections from the channel type structures that are formed with alpha cyclodextrin when they come together into this hexagonal lattice. Unfortunately, it's not something we could detect in our system. but it doesn't mean they're not threading. It is quite probable that because of the thiolate anions on the cyclodextrin, they can't come very close. They don't form the same sort of tight hexagonal lattice. We also did some small angle neutron scattering, which I'm probably going to skip unless people want me to talk about it, but just finished with the very last simple experiment to hopefully prove our point, because we could not find a technique that shows us without ambiguity that the cyclodextrins are actually threading onto the polymer, is that if we go back to the beta that we made at the beginning, we know beta is not a good host for PEG. And indeed, if we use beta in the same quantity as alpha, we do not get a gel. So that is showing that with alpha, it is probably threading, and with junctions made between cyclodextrins onto different chains, it formed these gels. With beta, it is not threading, and therefore we don't have enough beta to form a network if it's not interacting with the PEG chains. And with this, I will finish thanking the people who've been involved in the work that I presented here. This is a very brief summary of some of the things that I've said, just to say that this is quite a versatile motif, this interaction between PEG and alpha CD to build different things. With the copper sulfide, one other advantage that I didn't mention is that because it absorbs in the near infrared range, if you actually irradiate it with a laser, you also get gelation through the heat that is generated by the copper sulfide. So it's another interesting trigger that can be used. Thank you very much for your attention, and thank you very much for the invitation again. I'm ready to take perhaps one.
Okay.